Your heart's a magnet. Every time a muscle fires, moving ions produce a magnetic field. At skin contact, that field measures about 100 picoteslas. Your brain's magnetic field's even weaker, sitting at an incredibly faint 100 femtoteslas. To understand how small that is, we need to frame it against the environment. This vertical sensitivity scale shows a standard bar magnet at 0.1 teslas. If we drop down to the Earth's ambient background magnetic field, the one that spins a compass needle, we hit 50 microteslas. Plotting biomagnetism on this same chart shows the severity of the math. The Earth's field's 500,000 times stronger than your heart signal and 1 billion times stronger than your brain's. You can't isolate a signal 1,000,000 times weaker than the background you're swimming in by measuring absolute field strength. Classical sensors simply drown in the noise. The only solution's building a sensor that ignores absolute field strength entirely. You need a device that maps magnetic flux to quantum phase shifts. That's quantum magnetometry. It's the technology hospitals use to image human brain activity with millisecond timing, and it's how the Navy hunts submerged submarines. This technology has a classified layer. A CIA program called Ghost Murmur may be finding downed pilots by their heartbeats from hundreds of meters away. Extracting a faint femtotesla signal from a massive wall of ambient noise requires completely abandoning classical physics in favor of quantum mechanics. The foundation for the sensing architecture started in 1962. A 22-year-old PhD student at Cambridge named Brian Josephson predicted that superconducting electron pairs, known as Cooper pairs, had a unique property. This diagram shows two superconducting materials separated by a thin insulating barrier. Josephson predicted that Cooper pairs could tunnel directly through this barrier, carrying an electrical current without any applied voltage at all. His supervisors didn't believe him, but experimentalists proved it, earning him the 1973 Nobel Prize in Physics. The device is called a Josephson junction. By 1964, a team at Ford Research Labs took the next step. They wired two of these Josephson junctions together into a single superconducting loop. The result was the first superconducting quantum interference device, or SQUID. When magnetic flux threads this loop, the current oscillates. The oscillation period is 1 magnetic flux quantum, h over 2e. Mathematically, about 2.07 femtowevers. A commercial SQUID routinely resolves a tiny fraction of a single flux quantum. That translates to an operating sensitivity of roughly 1 femtotesla in a single second of averaging. But there's a severe operational bottleneck. A SQUID needs superconductivity to function, which requires extreme cryogenic temperatures using liquid helium at 4 Kelvin. That requirement dictates the physical footprint of clinical magnetoencephalography machines. They look like dental chairs with a 100-liter dewar of liquid helium bolted to the top to keep the sensor array cold enough to read your thoughts. While SQUIDs successfully shattered the classical noise limit, their reliance on liquid helium restricts them entirely to highly controlled laboratory environments. Physicists spent decades hunting for a room temperature sensor capable of matching SQUID performance without the logistical cost of liquid helium. The optically pumped magnetometer emerged as the solution, eliminating the need for cryogenics or exonic superconducting materials. Inside is a glass cell filled with alkali vapor. A primary laser polarizes the atomic spins, aligning them perfectly. When an external magnetic field disturbs them, the spins precess. A secondary laser reads that precession as a change in transparency. The specific variant that beat SQUIDs on raw sensitivity was demonstrated by Michael Romalis and his colleagues at Princeton in 2002. They created the Spin Exchange Relaxation-Free, or SERF, magnetometer. In a SERF regime, the vapor's heated to 180 degrees Celsius. This ensures spin exchange collisions happen faster than the precession, eliminating the dominant relaxation mechanism. A SERF sensor reaches an operating noise floor of 160 AttoTeslas, entirely contained inside a device smaller than a coffee mug. DARPA's 2010 QuASAR program and the follow-on 2013 AMBIIENT program poured massive funding into these atomic sensors and related quantum-limited detection technologies. Simultaneously, researchers like NIST's John Kitchen Group successfully shrank the entire assembly down onto a single microchip. Replacing cryogenic superconductors with heated alkali vapor moved sub-femtotesla quantum sensing out of the lab and into the field. This graph shows the reality of field deployment. Magnetic dipoles obey a strict law. signal strength falls off at 1/r². Your heart produces 100 picoteslas at contact, but at 1 meter, that drops to 100 femtoteslas. At 5 meters, the signal decays to roughly 800 AttoTeslas, falling below the single-shot noise floor of commercial sensors. Physicists use 3 specific engineering mitigations to push past this limit. First, mu metal shielding rooms attenuate ambient background fields by factors of 10,000. Second, a gradiometer geometry uses 2 close sensors to subtract uniform background fields, leaving only the local magnetic gradient. Third, building 1,000-element arrays allows you to coherently average out uncorrelated noise, buying a 30 times improvement in signal-to-noise. The military has applied these principles for decades. Since World War II, the navies used magnetic anomaly detection to hunt the distortions steel holes create in the Earth's field. Modern magnetic anomaly detection relies on these new optically pumped cells. Aircraft like the P-3 Orion and the P-8 Poseidon detect submerged holes at ranges measured in hundreds of meters. This hardware scaling provides the technical basis for the Ghost Murmur program. It's how the intelligence community may be finding downed pilots by detecting their heartbeats from hundreds of meters away. Distance isn't a hard physical barrier. It's an engineering problem solved by scaling sensor arrays. SQUIDs and SERF cells are part of a broader technology family. The sensing physics and the confinement physics are the same physics. A superconducting array measuring cardiac signals uses the same Josephson junctions, extreme cryogenics, and quantum noise readouts as a magnet stack. They're one shared technological cluster. Media reports have detailed classified fusion programs, producing anomalous FRC plasmoid orbs in the sky. Simultaneously, reports describe intelligence programs tracking human heartbeats from mountainsides. These accounts describe a single applied technology cluster, expressing itself in 2 operational directions. When Forbes argues for the existence of these technologies, he's describing a shared family of physics, not 2 unrelated miracles. Once you understand the underlying quantum architecture, the seemingly impossible claims of classified science look like standard engineering.